campaign mode.
Hello, everyone. Let's start with a simple question. How many of you are on call now? So many people are on call. Yeah, I highly appreciate your presence here. Thanks so much for coming. I'm Karthik. I work as a SRE at Google, and I don't count how many times I've attended LSPE, and it doesn't excite Devanshu so much, but I'm an ex-Yahoo, so I've been attending LSPE right from my Yahoo days, and this is my first time hosting. Yeah, that's great. Badri?
I'm Badrinath Ravindran. I think I hosted many times and I attended many times. I still remember the first one I attended in 2013. I was like super surprised, like what is this meetup about and other stuff. But whenever I come, I learn a lot, network with many people. So please do continue the same. I have very bad throat, so yeah, I think to continue.
Yeah, we are SRE team at Google. So what is SRE? Like, can someone talk about like just 1 or 2 lines about SRE? Anyone? Okay.
Service restart engineers.
Good one. Good one. Any other funny acronym? Slight reliability engineers. Okay. Anyway, yeah, we are the engineers who solve challenging problems. We apply software engineering principles to the infrastructure and reliability. And at Google, we are like a global team of more than 3,000 engineers, and we are business aligned. We try to bring the business value by partnering with various other teams. Sometimes it will be very obvious. Sometimes it won't be obvious. So when the site is working fine, like everything is working fine, it won't be obvious that there is a site reliability engineer who has worked on it. Yeah, it's not too obvious sometimes. And we are specialized in the production management, and our expertise is about reliability and system design as well. Capabilities. Yeah, the foundational being the SLIs, SLOs, and the error budget. We define the SLOs for our CUJs. And the other foundational thing is monitoring. That's a fundamental thing. We monitor our SLOs, SLIs, and see how they are performing. And incident management is about when there is a breach in the SLO, or like when there is a outage, we react to that. Yeah, usually like on-call people who are here, like if they get pays, you'll see they're running out of the room, and you can see the tension in their faces when the pager rings. So that's the foundational part. And other parties, like recently, like in last few years, the evolving parts are the observability. I've seen a lot of people working on the observability. Just about anyone want to talk about observability, like just 1 or 2 lines about that? What is the difference between monitoring and observability? I'll ask this question. Yeah.
Yeah. So observability can be defined or explained that the application or whatever is running, it should be able to you should be able to see what is failing, when is failing, and some signals to why that is failing. Monitoring is one part, but it also includes proactive and reactive monitoring, which can be logs also, tracing as well, statistics also. So multiple aspects can be included in observability.
Yeah, fair. Yeah, just to summarize, monitoring. You have one more?
Yes.
Yeah.
So monitoring is basically reactiveness to some extent.
and the observability is a little bit of proactiveness.
Okay. Yeah. So through monitor, yeah, one more.
So in observability, we see the pattern also, but monitoring gives us a particular time series data. In observability, we see the pattern and we can take the active action.
No. Yeah. Anyone else? Yeah.
So monitoring tells you like what is happening. Observability will tell you why it is happening.
Yeah, exactly. Yeah.
Yeah, so I work as a software engineer at Paytm. So I wanted to know that when we talk about SRE, so does it also include software engineers who are observing the platform, the release management, as you mentioned in the slide, or we should have a separate people dealing with the thing?
So in my team, like, all of them are software engineers except me. So what is happening in the industry and the company is like, software engineers are like mostly, transforming into SRE role also. As you mentioned, like, earlier, like, the engineering practices are pretty much common for software engineer and the SRE. The software engineers generally work for the products, like, features and set, but the SREs will be working on the reliability, capability, scale of problems and other stuff. But all of them use the same development methodologies, platform, CI/CD pipeline, everything is common. So whoever is recently clearing the interviews, most of them are software engineers. Yeah, into the SRE roles.
Yeah, it's just the same set of software principles that are being applied to a different domain. That's it.
The interviews are like pretty much like there are two tracks, but like the work is common. You can come as an SRE, work for an SRE. You can come as a software engineer and work for SRE. It doesn't matter.
Yeah. And other capability is change management, adaptive change management, especially. So you can't apply the same change management rules to everything. Let's say that there is a low risk change. You are sure that it's a low risk. So for that, the change management strategy should be different. It should go very quickly, like there is low risk. But there is a very high risk change. Then you need to apply a lot of principles over there that we talk in the next one. That is, how do you make sure that the rollouts are reliable? So again, like same, you can't apply the same principle that, hey, I will, I have 100 machines, I'll deploy and 25 machines in first hour, 25 machines in second hour. No, like it may not work always. So we should come up with different strategies. We should integrate our rollouts with the monitoring system, like roll out 1% of it, see how the SLOs are performing. And you should have the capability to stop the rollout or even roll back when there is a SLO breach. So you need to be adaptive in the release management as well. And the advanced capabilities are like performance and capacity optimization. Now the demand for hardware is like ever growing. So we need to make sure that our capacity is properly utilized. And there's a different set of engineering altogether on capacity itself. And that comes under the site reliability engineering umbrella. Resilience engineering, like you need to be like not crashing, you should degrade very slowly, and also you should have the resilience to come back up very quickly if there is any outage. So that's all about the resilience engineering. And AI-driven operations. I know everyone is excited when I say AI. I see a lot of AI ops folks. So just talk about one or two points about how AI can help SRE. Just one or two. Anyone? Error detection. Okay. Better. Pattern recognition. Oh, okay. Nice. Automated RCA. Okay. Nice. Anything else?
Cursor for on call also.
Okay. Okay. Log monitoring. Anything else?
Yeah, same done. So I was also saying log monitoring.
Okay. About anomaly detection?
Yeah, anomaly detection. Basically converting the time series into a frequency spectrum and then analyzing it. That's what
Oh, okay.
we're going to do.
Okay, nice.
Very good points.
Auto healing? Okay.
Imagine for yourself so that you can
Anybody in your company is like, using auto healing via AI on production? Seriously? I just wanted to see how far the industry has gone. Yeah. Some of them are very theoretical, I would say. Yet, like before a few years, if you asked me, like, I would have joked. Now I believe, like, at some point in time, it will be coming in. We ourselves, like, use it mainly for on-call, like several places, like, AI is very helpful. It can automatically.
Correlation of alerts, we can
Yeah.
we can build an agent for ourselves that can read all those emails and chats. That's level of this. That's the next level it can come.
And again, like, it depends on the human's decision making. It gathers the details and presents it to us.
Our agent we keep on training this.
Yeah. How about reducing the toil? Has anyone used AI to detect this? This alert is not useful, and something like that? Huh? Very risky. Okay.
Correlating different events like your code changes, multiple tools that you use, like AI can help. Again, it's not something that we're using, but that's how the visual part is. Like what you do usually when an alert comes in, and then you look at various different things, right? AI can help us detect that faster so that your MTTD, MTTR reduces.
Yeah, great points. I hope, one more.
So we have built a few MCP servers for the tools which we have in-house, which help us to do a correlation and troubleshooting of deployments, considering the logs and metrics and traces which we have. So that really helped us recently to save the on-calls time to go and debug what's happening.
So you use the existing LLM models, or you created your own model?
So we have a few which we built ourselves, and some of them are open source as well.
Nice.
A tool which helps us to relate the current incident with the past RCS, like how the past RCS learnings, like how the similar incident could have happened again.
You have an in-house incident management tool or a third party?
No, we have an, it's hosted in-house. It's a bought fork from a repo, from an open source repo.
We correlate alert with switch.
Yep. We have integrated with bug management, incident management, all of this. It pops up like, what has happened in the past or what is currently happening. Is it correlating to this or that? It presents with a lot of information. It's very easier.
Okay. Yeah, so our mission is to improve the reliability, efficiency, and velocity. So velocity is the one which delivers which is like delivering more business value. Velocity is a change. So change means like new features getting launched. So that's a change, and that brings the business value.
So one person asked, what is the difference between the software engineer and SRE? So this is one of the main difference. As a mission, the SRE's mission is little different from the software engineering, generic software developers' mission. So we don't focus on the product features, rather we focus mostly on the reliability, efficiency, and the velocity. Right? Suddenly, if you want, like, hey, I want my product to run in the entire globe. I just want to scale from 100 kps to 1 lakh kps. How do I go about it? The SREs pitch in and they take the product to that velocity.
Yeah, this is like a graph. So if there is no change, there is no need of reliability. Like systems will be stable. Like hopefully, if there are no hardware failures, they'll behave as it is, and then like the error budgets won't be high. But if there are too many changes, it can risk the reliability of the system. So our SRE goal is to make sure that we still make the changes, but still make sure that it is reliable. So we are at somewhere around, we are aiming from going from point B to point A here. So that's our mission. And also, I forgot to talk about the efficiency. We need to do all these things at a very low cost. We can't have a very high cost for delivering all these things. So we care about the efficiency as well. And yeah, and the final thing, so we are growing in India. Like there are a lot of teams that are there, as you can see, search, ads, YouTube, devices and services, and Google Cloud. So these are all like some of the engineering teams that are there at Google India, and we have SRE presence for some of the products, not for all, but we are growing. Yeah, thank you. And thanks for attending. So as a token of appreciation, you'll get some swag when you're going back. So please don't forget to collect that.
Oh, sure. I mean, people cannot actually. PTM is not very good news. That's most important.
So we have a lot of talks lined up here. So Bharat, who is the first one?
Yeah, we have maintaining reliability for AI inference platform by Gaurav Sharma and Sainath Reddy. Okay.
Enjoy your day.
Thank you.
Okay, Google Meet and then share.
Yes.
But can I get
You have script this. Yeah, you can.
Oh, so we can share particular screen.
Yeah, you can share particular screen. You can share the entire screen. Or
So hello everyone, good morning. Meanwhile, the setup is going on. Do pardon us, this is our first talk that we are giving, both of us. So, we are both SREs at NVIDIA right now to the AI inference platform under DTXC Cloud. And I had been SRE for Adobe Analytics, VMC, VMware Cloud on AWS, Azure Compute, VMSS, then NVIDIA GeForce Cloud gaming platform, and then right now at Inference. So we have tried to like summarize the content, trying to thinking like it might be helpful for everybody, but let's see how things goes.
if you want to share complete screen, you can share.
But also, I was on call this week, so I was hoping we'll get more time, but yeah. Even as F3 was very tricky this time with log loss. So, I mean, sometimes teams recommend, like they demand 100% log availability. I mean, how do you tell them how is that possible, right? So, yeah. Anyhow. So I've given my introduction. Sai, I think we can start.
Hey, this is Sai. I'm working as senior SRE at NVIDIA. So it's been 2 years with NVIDIA. So we are working on in serverless inference platform. So now it's part of DTXC Cloud. Earlier it used to be called as PCF.
So yeah. Okay, so the topic that we have is maintaining reliability for AI inference platform. As of now, I think this is one of the very crucial aspect of software systems. And we'll start with a bit of introduction about AI, what is inference, what is model training. So when I think about AI, the first thought that comes to my mind is about Jarvis, the assistant which Iron Man had. And when the movie came out in 2008, it was almost impossible to think about it like everybody would be able to access such an assistant, right? The idea is that you give an order, the machine or system will think about all the steps, then they'll execute it, and then they'll give you the result, right? And today, I think it's possible. We all are using a lot of tools, probably not in production for SI, but for a lot of our day-to-day work, right? So AI is basically any system that can perform tasks that would typically require human intelligence. We can categorize it into two parts. One is model training, the other one is inference. Model training is, I can give you an analogy of my toddler who is learning about objects and colors by looking at his books and various objects in the real time. And similarly, in software systems, it's algorithms which are learning from the huge data sets. Now, I wanted to give the same analogy for inference, but the problem with my toddler is he will only respond, not always respond to when I ask him, he's only respond when he's in mood, right? But in case of inference, it's basically you give the real-time input and the system refers to the trained models and then generates an output. And I think we all have been using it. The simplest example is ChatGPT, or even nowadays Google search, when you do the first thing that you see on the screen as a generated output. Right. So that's basically inferencing. These are some codes that I liked, and so I added here. This came up in the earlier discussion. So I think not for SI, though everywhere, but AI is no longer just in R&D, it's in production. And that makes things more critical for SIs because model or inference is only like useful if it's reliable. For example, if your email provider has a filter for filtering spam messages, but they are sending good messages to spam very frequently, you'll disable that filter. And this doesn't only incurs cost to the organization, but it also like loses end user confidence. So you might not be able to use the next version of it, even if it is an advanced one. And the last one here is like inference failures aren't academic, they are customer facing. So reliability becomes very important in these aspects. So we can move on to how an inference request cycle goes through. As the graph here suggests, like as the diagram here suggests, there is an input, there is tokenization, then processing at the GPU level, then detokenization and out. So input can be anything that like, it can be text, it can be audio, video, or a document. Tokenization basically means converting that input into something that model would expect or model would understand. It can be an array of vectors. Sorry, it can be a vector of numbers or metrics of numbers also. On the GPU level, basically, we should have model weights first because that is required for basically attention layer and feed-forward nets. And GPU has to load in the model in the memory during the processing. And then the first thing that starts here is the prefill phase. So prefill phase is when each of the tokens which are generated from input are processed and one new token is generated. Then all the new tokens which are sequentially generated, they are again added back to the processing and the new token, again a new token is generated, right? So prefill phase is the first new token that gets generated. Decode phase is when all new tokens are generated auto-regressively. So which means that one token at a time is generated, but each new token depends on the previously generated tokens. Okay. Now, why I talked about that was because from the infrastructure perspective, why do we need GPUs for inferencing when we have CPUs as well, right? So the difference between GPUs and CPUs is GPUs have thousands of cores which can perform simple tasks. CPUs, on the other hand, have lesser number of cores. So as I mentioned that during the prefill and the decode phase, there are a lot of operations which are expected because one simple question can have multiple tokens and then it would generate based on the response, it will generate a lot more tokens, right? So you will have to, for a single inference request, you will have to process a lot of operations. And when you are dealing with multiple requests, then again, the number of operations increases. So it makes sense to use GPUs where you have a lot more cores and they can batch together all the requests and then perform those operations and give you a response faster. Also on GPUs, they have higher memory bandwidth. So that is all. And based on these criteria, I think industry adopted GPUs and there are a lot of optimized frameworks as well available on GPUs. Okay. So how do we do, like if I have to run inferencing on a Kubernetes cluster, say a vanilla Kubernetes cluster, what is different? I think we all have been, most of us would be using Kubernetes from a long time now and mostly using the CPU nodes. But when GPUs come into picture, how things change. So I try to put a flow chart here. So first step would be to provision the Kubernetes cluster, but this time we would also have a node pool for GPUs. The next step would be to install something to manage the GPU drivers as well. And then one more thing, we would also need CPU nodes because we would want to bootstrap the Kubernetes cluster, right? So we would have a lot more components which we would want to run on nodes where because GPUs are also expensive, right? So we would utilize the resources from those nodes. So the next step would be to install something like a backend server to serve the request, which can be Triton inference server, K server, etc. Like nowadays in open source, there are multiple options. And the next important step is having the model available for the GPUs to load in memory whenever they are serving these requests. Okay, so the last would be exposing the service or the server via an OpenAI compatible endpoint so that this can be consumed by whatever the client is trying to access it. I mean, simplest thing we can do is expose it via Kubernetes service, right? So, yeah. So I tried to put in some aspects which would make GPU enabled clusters versus CPU only clusters. So I tried to put in some of the aspects here. For example, node type, pod scheduling, device plugins, driver installations, container requirements, monitoring, etc. So I think one of the key components that we have noticed while we are like, what would be different from CPU only clusters is like I tried to put in here, and one of the key components is GPU operator. I think what makes using GPUs very easy is the GPU operator. You can deploy it directly. It's open source. You can just deploy it via Helm deployment. It takes care of almost everything. It will install all the required drivers, all the required also like advertising GPU as resources, and even the monitoring tool. And all you need to do is then it's kind of a plugin. It makes GPU usage as plug and play, right? And these are the key components. Like GPU operator will be the operator which will deploy these key components. Then you need a device plugin. So whenever we add a resource to a Kubernetes cluster, if that can be a storage resource as well or other resources, we'll use device plugin which would advertise those. And then it will also install GPU drivers and container toolkit. So GPU driver is important to expose the GPUs to the host OS of the node. And then container toolkit is required to expose the GPUs to the containerized environment, the workload which is running on the containers, right? And then DCGM exporter is a utility which can be used to expose the metrics, right? Because we all need observability, and based on that only we'll be able to do various operations, right? So I also wanted to add here, how does a GPU becomes allocatable in Kubernetes cluster? So you can say the node boots up with GPU hardware. GPU operator we are assuming here is already installed. So NFD is a tool, or node feature discovery is a daemon set which will run only on the GPU nodes. It will come up and it will discover, hey, this node has GPUs on it. And subsequently, there will be other components, some schedule jobs or daemon sets will be installed on those nodes. Then there will be driver daemon set that will run on all the GPU nodes, which will install the required drivers. And then container toolkit. Now, in the last slide, I had mentioned about the purpose of drivers and the container toolkits, because driver is just to make the node aware of, or the node host aware of the GPUs, and container toolkit is to pass through the GPU resource, the containers. Okay, and the last, second last is device plugin daemon set that will again advertise the resources to the Kubernetes, and from there you'll be able to see, even by describing a node, how many resources are available, how many GPUs are allocatable on the node. And the last is DCGM exporter. So that's basically for the monitoring. It's a daemon set which will run, and it will look at all the fetch all the metrics and expose them, which can be fetched again by Prometheus and shipped accordingly. Yeah. So next, I would hand over to Sai to cover some more details on the
Sure. Thank you, Gaurav. Thanks for setting the context for me. So we have talked about provisioning GPU clusters and bootstrapping them to host AI workloads. Now let's talk about the reliability using SLIs. So SLIs, if you are new, they are service level indicators, a quantitative measure to measure health and performance of a system or a service. For example, request latency. How long it takes to return a response to a request. So that one can use as SLI. AI inference platform observability differs from traditional approach. In inference platform, we have to include special hardware metrics like GPU, TPU to identify any service degradation or to figure out any bad user experiences. DCGM, it's a data center GPU manager, provides these metrics, and these metrics can be scraped and export it to your observability platforms like Prometheus, Thanos, etc. Also, if you're provisioning your GPU clusters in cloud providers like Google Cloud, so you can go to their logging and monitoring services and get these metrics and use them as SLIs for detecting your GPU software and hardware issues. Let's talk about availability. Okay, let's see. Oh, yeah. So it's not about it's not about AI system being available, reachable. It's about the whole entire chain being ready to perform inference correctly. So I'll talk about. So we have we have listed 4 categories here. Uptime of your inference endpoint. So this is the classic measure. Are the API endpoints reachable and returning successful status codes? This is our baseline. Next is specific to the inference platform, model load readiness. So endpoint is useless if the model is not loaded into GPU memory and ready to serve. So we must track the time it takes for models to become active after a deployment or a cold start. We'll talk about cold start. GPU node health. So the underlying hardware is a common point of failure. And we need SLIs that track the health of individual GPU nodes, watch for hardware errors, overheating or unresponsiveness. So we have seen multiple issues with coming from unresponsiveness. We'll talk. High availability. So for any critical service, as we measure the health and availability across multiple availability zones or regions. So an SLI here could be the percentage of healthy replicas available at any given time, ensuring resilience against localized failures. Let's talk about latency and responsiveness. So speed isn't just number. It's the difference between users staying or leaving from your product, whatever it can be. So for inference, we have new set of SLIs. So let's talk about the first one. So TTFT, time to first token. This measures how much time your platform has taken to respond to user inference request. So, for example, showing a blank screen versus I'm thinking. Generally, we should target under 200 milliseconds faster than a human blink so that user don't see the difference. Next one, time per output token. So once we start responding, so let's say we put I'm thinking, how smoothly do words flow? So if it takes a lot of time for the response to come, so user feel bored and they'll give up. So choppy responses feel broken even if technically they are correct. And one thing I want to highlight, so this dashboard I have taken from Grafana dashboard sample. It's not it's there. I will put the screenshot also. So the one thing I want to highlight here is end-to-end latency, top right. So this is the difference. When we measure end-to-end latency, so let's say you are having spike of inference requests which came to your system, and auto scaling, obviously we'll talk about auto scaling also. So it takes some time, right? So in the meantime, the inference request sits in the queue. It can be your Kafka, SQS, or NATS. So the amount of time it has waited in the queue plus actual inference time which your K-server or Triton server takes, plus let's say if text to video. So if there are any media assets which we need to put somewhere in the bucket, cloud bucket, or anywhere someplace. So that post-processing time, from queue time to post-processing time to like the point when we give a response to the user, so the whole time is taken as end-to-end response. It's not typical like request response. So that's the one main difference. So when you calculate end-to-end latency, how user is how good is user experience, you can rely on this. And obviously there will be some network service sets. So let's talk about cold starts. We measured the delay incurred when a request hits the cold replica, where the model is not yet loaded into GPU memory. This is especially important if you are developing a serverless or scale to zero environment. So if you go to Cloud Run in Google Cloud, so you have this option where you can keep minimum instance as a 0. Like if there are no requests, your nodes will be downscaled to 0. And when there are requests, then Google Cloud brings instances, and there are a couple of configurations which you can use, like CPU boost, to decrease the cold starts. And there are a couple of strategies which you can use. Pre-bound strategies, model caching. So model caching, so there are some models where we have seen models in size of TVs, 1 TB, 2 TB. So having a model caching solution next to your cluster will help a lot when your application is auto scaling. So when the new workers are adding. So there is an auto scaling session we'll discuss there. And obviously keep alive policies help minimize cold start penalties in production deployments. So, and error rates and fault tolerance. So failures in AI systems are complex, ranging from network issues to GPU specific problems. Our SLIs must capture this, and we need to answer the question: how gracefully does your system fail? So typically, when we say error rates, typically we talk about 5x. This is the standard measure of server-side failures. So apart from this, specific to GPUs, out of memory, CUDA out of memory errors represent one of the most common failure modes in GPU-intensive inference workloads, typically occurring during traffic spikes when batch size exceed your available GPU memory.
Caching that you were referring to is memory caching or disk caching?
Disk caching. Infrastructure falls. So the node failures and pod eviction comes in this track. We track the impact of involuntary disruptions like node failures or pod evictions on overall service health. Kubernetes pod eviction policies designed for stateless workloads can be catastrophically impact your multi-GPU inference jobs that require coordinate resources allocation across multiple nodes. Gang scheduling, priority class configuration help protect critical AI workloads from resource contention and unexpected evictions. Sorry, I have one slide which I took for 5 minutes. So this one more. Yeah. So there's a another slide. So scalability. So AI workloads can be incredibly bursty. So scalability, SLI tells you how well your platform adapts to these fluctuations without compromising performance or cost. Key factor includes HPA. So, but here we have different metrics which are GPU aware HPAs. So these are your GPU utilization, inference queue length, how many inference requests are waiting in a queue. So based upon that also you can scale your nodes and model specific throughput indicators. So they provide more effective scaling triggers than traditional CPU memory based metrics. Load balancer GPU scheduling. This involves ensuring that your incoming jobs are routed to the most appropriate GPU resources. So there are open source parts like Orion, which can enable fine-grained GPU sharing to improve throughput, co-locating multiple jobs on a single GPU. And batching for non-latency sensitive workloads, batch inference is crucial for efficiency, and we can measure batch size, processing time per batch, and overall throughput to ensure we are maximizing GPU utilization. So capacity and resource management, you folks know GPUs are expensive and there is limited capacity, and wasted capacity is wasted money. The below SLIs, they ensure we are efficient. So GPU utilization and bin backing. So we aim for high utilization without crashing performance degradation. Fine-grained sharing techniques allows us to bin back multiple smaller inference jobs onto a single GPU, drastically improving performance. And yeah, model memory footprint. So one must monitor the memory consumed by each model to ensure it fits on a target hardware and to inform scheduling decisions. So auto scaling, we have talked a couple of points earlier about the metrics, but yeah. So what happens when you run out of GPUs? We need SLIs to track length of pending pod queues and time request wait for resources. Scenarios with pending pods due to resource starvation can unnecessarily extend lifetime if not managed well. Yeah, so last one, observability. Finally, none of these SLIs matter if you can't see them. Observability is the foundation of SRE, as like we all know. So one thing is you need to get fine-grained metrics. So DCGM provides them. You can scrape and you can use. And we need deep visibility into GPU subcomponents, including compute, memory, power consumption, to understand performance bottlenecks. Latency histograms, yeah, instead of just averages, use histograms, which shows us the full distribution of response times, helping us to identify and debug tail latency issues. Model level logs and tracing. So logs must be tagged with model names and versions. So tracing should follow a request from your endpoint, so load balancer or gateway through inference engine to the final response. So you can see where the particular inference request has taken more time and debug further. So it's pretty useful for even hardware isolations also. So if you are monitoring, your metrics are not supporting, so you can fall back to your traces and figure out a bunch of faulty nodes which are having, let's say, GPU specific errors, XID errors, hardware errors, and you can card in and you can take care of them. Yeah, so last one under the observability. So have saturation signals to monitor your system overload, such as pending pods in Kubernetes or length of GPU work queues, to act before system fails. And so that's all from side. So you can see here, I haven't talked about dashboard, but these are self-explainable. So here, the queue size I was talking about, small, but yeah, I'll upload we'll upload the slide. You can go through. So there are pretty useful metrics here, which will give you how your cluster is, and you can take actions. Yeah, I think, yeah, that's also, we have covered these SLIs. I know this is mostly theoretical. Maybe next talk we can show how we are dealing at NVIDIA. So we do use these things, whatever we talked, and there are other things also. Yeah. Yeah.
So by this talk, what we were trying to portray was Kubernetes has been there, workloads and has been running on them. But what we have seen is when GPU came in, things changed drastically. I mean, you cannot do the rolling over upgrades in the same way. You cannot just kill the pods. There was a time where on a cluster, I had just deleted all the workloads because the tool managing it was not working. And it took almost 2 hours for all the models to be downloaded again and then bring up workload. So a lot of new problems come up. You cannot just roll over, you cannot just upgrade the nodes right away that you would do because you don't have capacity or quota. And wastage is one of the key metrics that has to be looked out, because if your resources are not using it and those are reserved or blocked. At times, what we had also seen was everything is working fine. There is nothing visible, no visible error, and yet the workloads are failing. Reason or the requests are failing. There are hardware errors within GPU, which again had to be depicted, right? So we can use Kubernetes with GPUs, but things change drastically again. And I think we are going through the same maturity pattern that we had gone earlier. And I'm hopeful that with the community and various open source tools as well, things are going to improve in time. Yeah, that's all. Thank you.
GPU operators, better interface. What is the resources overhead for using GPU operators?
It's not much like what we have noticed, it's not a lot of resources that they would use. There would be some overhead because it would run some components, but those are necessary. Without those, you'll not be able to run your workloads.
So there would be a significant difference in scale. Suppose I'm using 2,000 clusters and I'm using operators.
See, operator will have deployments in daemon sets. So if you have 1,000 nodes, then you will have 1,000 replicas of those small containers running. But those are required because if you don't have the driver installed, right, it will not be passed through to the container workloads.
Okay. And regarding the serverless, so serverless is there are not unlimited servers. What is the hard limit at the back end you have for the serverless?
No, so it's not about serverless. This was about general basic scenario, but serverless again, I mean, it's like a cloud platform, and there is always a limit in the cloud platform, right? Because you're running in somebody else's data center.
It depends on your quota. So if you reach out of quota, you need to contact your CSP and then ask for increase in quota.
So in your auto scaling, other than CPU and memory, what are the other parameters you have used?
So DCGM that we mentioned, like it exposes a lot of utilization metrics on the GPU side as well. So those can be used. So that's why you will have to have GPU aware auto scale.
And for downscaling, for graceful termination, what are the algorithm or something which you have used
for graceful shutdown? Like you cannot kill the pods immediately, right? If some processing is happening currently. So in that case, how you have handled the scenario?
So graceful termination again would depend on the server you're using for running the request, right? That will handle that part because the queue of the request which would be there, it would be managed by the server that you're using, like Triton Inference Server, KServe. So if you're using those, then that will be handled by that tool. So not by us.
Yeah, one more way is like you can look at your inference server like Titan. Are there any active jobs which are getting processed on that particular cluster? If there are none, then we can go on. Like the question is if your decommission cluster, like what is the deletion factor? So we will typically check what are with metrics, DCGM. So we check how many active jobs are running inside there. If there are none, then we give signal saying, hey, go on decommission. Sorry, I missed that.
Thank you.
So concepts are same, but implementation is a bit different. Yeah.
Hey, I have a question on, say, SRE who is very well versed with the observability and monitoring of CPU-based workloads. And I understand that the fundamentals are the same the latency and availability rates and etc. What are the knowledge gap do you see somebody who is very well familiar with CPU but have absolutely no idea about GPU? Is that like there's a huge learning curve involved in understanding how the GPU works and AI inferencing and other stuff? What is the knowledge gap and the learning curve?
So in my personal opinion, what I did was, we run a gaming cloud as well. Then GPU can be used for multiple things, right? Gaming, model training, inference, and Sridham is here. I think his team manages for mostly model training as well. The key thing is like, what are your end user journeys, like critical user journeys? That has to be defined. And then while monitoring those, what more tools can we leverage, right? For example, like Sai mentioned that in this case, model readiness is also one of the key parameters. So what you will have to, if some knowledge gap would be based on, okay, what are the expectations of your users? And then you'll have to follow from there, okay, how can I monitor this? Like there can be multiple events. If I am making an inference call, right, then that can, where is it failing, that all that scenario, I'll have to note down what are the events. And then for all those events, which tools I can use right away, which other tools might be there. What I had to read a lot about was the GPU operator thing. That was actually completely different. So I started reading about it. That helped me in that scenario, and DCGM as well.
So one question. Here you mentioned only the SLI parts of the inferencing platform. So how you measure the SLOs and what is the any value on those SLOs? Can you talk about those?
So if you look at here, right? So we thought like how to portray to a group of SREs that what is different for CPU enabled and GPU clusters, right? Or for inference specifically in this case. So we can call these as so we thought let's just put the indicators which can be helpful, right?
Yeah, these are objectives you monitor.
Yeah, objective is basically you can say, okay, can users access the inference service? So within this objective, we have these indicators or pointers on which indicators can be built, right? And then SLA is basically the agreement that we'll set up, right? Okay, can users, 99% of the request users should be able to access.
Yeah, do you have any slide for SLO and SLO?
No, SLOs, no. So it's not separate. It's dependent on your service, right? How, like, what's your promise to the customer?
Yeah.
If you are very
that's again another, and also based on the hardware model, it will be different, right? For different architecture, this will be differ.
Yeah, that's why we try to keep it generic.
So that's that slide I was looking for. Okay, no problem. Thank you.
Actually, we didn't present it as a case study. Like we did it in a personal capacity, so we thought to keep it general. Yeah.
Done any comparative study for running the same workload in a CPU versus GPU? What is the performance metrics? Change in the performance, obviously it would be higher when you run it on a GPU. And what is the increment in the cost? Percent, I mean, from same workload on CPU, same workload on GPU. Those kind of comparisons.
Yeah, so I think we have not done it, but multiple organizations have tried that. Like I think there are a lot of people also trying to bridge that gap, and they're trying to do optimizations on how they inferencing or model training, all that happens, right? So I'm not aware of it, I would say, but people are trying it. I think there are blogs about it, but it's the general thing that we have shared. Right? I mean, obviously,
was there any improvement in the operational efficiency apart from the cost?
So We didn't try it, so I cannot say like there was operational.
All right.
Implement and operational. Yeah. Hello.
We are again the time. We're already half an hour late. We'll take more questions over Discord channel. Please feel free to ask questions. We will. Thank you so much.
That was Gaurav and Sainath. Thank you so much. That was so much of insightfulness for us. Next, we have Database at Scale, Cloud Spanner by Jay and Shirish.
We will do a lunch break after this.
Yeah.
Keep the mic close to you.
Yeah, this much is. Yeah, request the speakers to be on Discord. I think. Even I would be on Discord.
Hello. Audible? Just hands up. Okay. So hello everyone. I am Jay from Google. Okay. I will start again. Hello everyone. I am Jay, working at Google as SRE. I am from Cloud Spanner team itself. So we will be talking about database at scale for Cloud Spanner. So let's begin. So we have a short but a brief agenda here. We'll go over the introduction and few of the basics of the database. So, like, what's Spanner? Spanner is a backbone for relational data storage at Google. For Google services serving 3 billion QPS. And Spanner is in production for more than 10 years at Google. What do we manage? Like Spanner is a fully managed, globally consistent relation database service. So customers don't need to care about their data sharding, resource provision, etc. What do we mean by globally consistent here? Writes in, let's suppose, India are atomically consistent at the same timestamp in US. It's a transactional database service. So it's a globally shared database with linear serializability. In transactional database, linear serializability is a bit difficult, which Spanner provides it with ease. It's compatible with SQL Dialect, Postgres, Cassandra, or Google SQL. So let's focus on the logical database, logical data model of the Spanner. In Spanner, logical data model starts with an instance contains a database. Very simple thing. A database has a tables, then table have a rows and columns and so forth. One interesting thing here is range of rows are split into groups. We'll talk about this in a second. A single instance can span multiple zones, and multiple zones form a region. Very simple analogy here. As we talked about the data model, let's focus on the core data model and interleaving a bit. So we all know that powerful feature of the database is joins. They provide a robust way
to relate data across different tables using foreign keys. Typically, when using foreign keys, we are querying both of the tables which are involved using joins. In transactionally centralized database, this is usually very efficient. However, this becomes a significant challenge when we are dealing with globally distributed database. For efficiency, we want these tables to be in same server or close proximity. Because we are fetching data from the vast distances between two servers, it introduces a significant latency while querying the database. Now, the solution for this is interleaving. Now, this is very unique way to do shard the data counter database, and it's incredibly beneficial. How the interleaving works is, we'll go over the, we have two tables here. One is singers and the other one is albums. Generally, you would join these two tables using a foreign key and a primary key. But with interleaving, the rows are interleaved. So by interleaving, two different tables reside in the same server in the same data partition. This effectively bounds our joins to the same interleaving, bounds our join to the nearest proximity. So this would improve our performance drastically in globally distributed environment. So this is how interleaving would look like. So the first row of the first table would go first, and the second rows of second table will go down. This is, you can consider this as a directory in Linux file system, a very similar approach here in two tables. I hope I'm audible to everyone. I would take it as a yes.
How does it help?
Just a second. We'll take questions at the end. Now, once data is interleaved, we can do more with it. We can split the data and essentially shard the data very efficiently. Now, let's talk about the splitting of the data, basically how the data is sharded. Now, traditional database would face challenges in scaling in production environment. Significantly, when you are scaling a traditional database, it would reach to its limits because of its vertical scaling nature. And it would be a bit difficult to scale it horizontally. Now, as we talked about, his approach to this is splitting the rows itself and making it interleaved structure. And then we can have contiguous rows together. And the splitting would be done on the contiguous rows. Now, the key advantage of these splits are these splits can move between two different servers or two different data partitions altogether, or the physical boundary itself. And the splitting is done with no manual intervention or user knowledge, and it's done based on the database usage. Moreover, a spanner database can have thousands of splits, and it would just add to the performance. Now, once we have the data splits and basically our database, we need to consider its logical placement. Now, in Spanner, an instance is logically configured in regional, multi-regional, etc. But base regional configuration consists of 3 read-write replicas spread across different cloud zones. Now, each replica is a full copy of its database, which is able to serve read, write, and requests. So if one zone goes down, there will be other 2 zones serving the writes and reads, and so on and so forth. Now, moving a step ahead is that we have multi-regional configuration where servers are replicated across the same continent. In this configuration, instance would be replicated in 2 different zones of the same, 2 different zones of same 2 different countries in same continent. So meaning a a region would have two zones for its replication, and two region comprises of one instance. And there would be one more replica in the third country outside the continent. So this replica would be witness replica, which would aid to the voting count in the Paxos group. We'll come to Paxos group in few slides ahead. Now, one more thing is that when we are dealing with distributed database, we need to distribute our data accordingly or shard our data very efficiently so that it's available to clients with good performance and low latencies. Now, globally distributed, how do we segment this very efficiently is with geo-partitioning. It would allow us to further dissect our data and put it to closest to the client. Now, this strategical placement would allow users to define where should their data reside in multiple geographic locations. Now, let's consider an example. We have a Google Pay system or something like that, where users are originating from India. So our data placement, best data placement would be in Indian data centers. And we are launching our new service in Singapore or something like that. So our best data placement for Singaporean users would be in Singapore. There is no point in putting Singapore users' data in India. Moreover, now if I'm suppose traveling to Singapore, but I use Google Pay and my data would reside in India, the writes would be still faster because I am coming from a same geographic location, but Spanner knows where my data is. So it would just intelligently query my data from the Indian servers. Okay, let's visit now. Moving ahead is distributed systems, and we will talk about these basics of CAP theorem. Now, what CAP theorem states is in distributed data systems, we can only guarantee two things, either consistency or availability. And it comprises of basically three things: consistency, availability, and network partition. Now, network partition is something which would be like a naive term referred as a network outage. But I will explain that in a minute. So basically, CAP theorem tells us when we have a network outage, we can either prioritize consistency or availability. In traditional data systems, we often have prioritized availability over the consistency. Now, this is where few of the terms like eventual consistency is introduced. So, which means you will get high uptime and eventual consistency in the minutes. Now, the goal of the spanner is to achieve global strong consistency. How do we achieve this? Is a simple answer to this is using a global timestamp. But it's with a simple solution, it introduces one more critical hurdle, is that synchronizing clocks between two different servers itself is difficult, let alone we are going to synchronize each and every server on the planet. So this will introduce a hell lot of problem. So the solution to this is a true time API. Now, what is true time API? True time API is highly accurate, globally synchronized clock service that addresses this particular issue for distributed systems. It's consistent and reliable across geographically dispersed servers. Now, why we need a timestamp, you might ask. So timestamp would be used in commits. Basically, when you are writing the data, you would commit to the database. And when commits are there, we will use a timestamp. Now, this timestamp is selected as later than the latest prepared timestamp of any of the involved participants. We talked about the leader and Paxos, and we will talk about the participants as well in the Paxos slide. just bear with me for a minute. Now, this timestamp would be latest of the timestamp of any of the involved leaders, involved partisans, sorry. This will be helpful in achieving the external consistency. It means that anyone anywhere in the world transaction appears to have a single globally agreed upon timestamp in a centralized system. Now, after picking a timestamp, there is a brief built-in commit wait period. You might ask why wait. Is that explicitly for true times, tiny delay and uncertainty interval, we introduce a commit wait time. This would give us the catch-up time for the lagging servers, let's say. Now, I talked about Paxos a bit more in the previous slides. Let's come to the Paxos itself. What is Paxos? It's a family of consensus algorithm. It's not just one, but many algorithms put together. So what it is, so imagine we have a distributed group of processes, let's say servers or different computers together, and we have to make them all agree upon the single value to make any decision for the next action or something like that. This is what Paxos helps us with. It's a robust and fault-tolerant system, and even if some of our servers fail to answer, it will ensure that all the remaining available servers agree upon a single thing. Paxos has basically three different roles in it. The proposer, participant, and the learners. Proposers suggest a value to be agreed upon. Participants are there to vote to accept a proposed value or not, whatever they wish to do. And learners is a simple way to find out what value was ultimately chosen. If you connect the analogy here, a proposer would be essentially count to the leader. Participants would be the voters, the other remaining servers, and learners would be the lagging behind servers which are there. Now, as we saw that Spanner divides its data into splits, and we can just call them as a group as of now for simplicity. Now, these are small chunk of data which are grouped together. Crucially, each group would represent as a Paxos group, which would essentially do all the three roles. Now, within each group, a leader would be chosen, and leader would do all the necessary things for the transaction. Now, leader would be essentially important to coordinate the transactions within that group. I hope we are connecting dots till now. So now we have the leader, we have the transaction, we can now write through it. But this would again introduce one more problem that, as I said, I was traveling to Singapore. Now it would reach the Singaporean server, not the Indian server. Now my experience would degrade because I am facing latency. The simple answer to that is that what if my client directly hits to the Indian servers, reducing the network hops? So this is where the leader-aware routing comes into the picture. Now, what it does, it's a simple mechanism which improves the latency significantly and directly forwards my request to the leader region of my group. So this will allow me to query my database in much faster rate than the previous one where leader routing was not enabled. What?
Leader will make a part to India data.
No, direct India region. Because, yeah, direct India region.
Leader itself in India.
Leader itself is in India, so it will direct go to Indian region. If it's in Singapore, then it will go to Singapore. What?
Because you are in Singapore, you are calling Indian.
But then it will call to Singapore, then it will forward to the Indian leader.
So you're reducing only calling to Singapore and that.
Yeah, exactly. Exactly. So this will all happen in a client where I'm calling from. Yeah. So it will go again to the API, front-end API, and then it will go to internally route. Just a second. Now let's talk about the performance. Okay, sorry. So with all this, we can achieve like 22K QPS on regional instances. We have one more flavor of the instance configuration is the dual region, which can achieve 15,000 QPS in the dual region and 15,000 as well in the multi-region, where our data would be separated across two countries and same continent. These are the writes for the our instances. When we talk about the these were the reads. When we talk about the writes, it would be around 2.7K for dual region and multi-region, and 3.5K for regional instances. So, yep. Before we start the questions,
We talked about interlinking. How does that help in performance? In comparison to join status? Yes.
yeah. So what you do in interleaving is that you have two rows, right, from different tables. It will interleaving would help to give the two rows exactly to you. And so when you do a join, you do a full table scan, not full table scan. If you don't have warranties, then you will do the full table scan. But when you do a join, you will just scan that range of the row in the relational table and query that part of the data and put it with the primary part of the data. And with interleaving, you don't have to do it. It's already done for you. Like it's a directory structure where the primary key of the first table would be parent. Then the secondary, like the secondary key, you can say, is a child of the primary. Yeah, data is stored in that normalized form itself. Yeah, exactly. I can go to that slide. Yeah, this way. So these are just two tables. It would grow eventually if you have multiple nesting of levels. And now, generally, when I first learned this, I was at a question like, what if my two tables are not even related? Then even that would be follow the similar structure, but that would not have interleaving data because two tables are not even related. So there is no need to put them together.
So in I think the principle here is like if you want to query an author, you likely want single detail as well. So instead of, you want both the data to be on the same server. Instead of if it's globally distributed, you only be across two data centers. So similarly, a data are on the same server, same data center, same that type of thing.
So this normalization of data will happen in runtime or will be stored.
So it's defined in the schema. So yeah,
That's how it's stored.
yeah, you can see the schema there, right? In the albums table, the last line interleaved parent singers.
So here, how do you fetch like two sets of related data? They are clubbed together. Of course, that makes it easier. But still, there is some fetching mechanism like a join.
Yeah, in your query, you still use a normal inner join or whatever. But then the query executor will make the query plan knowing that this data is interleaved. Using the histories, it optimizes that so that you don't have to go across servers.
There are kind of splits which you have.
Yeah.
Yeah.
And then the advantage is when you actually when you have large corpus of data, you won't split again. It's much easier to split again because no data needs to move because it's already organized. It just all in the format. So even it's easier to split and move
How
data.
about the storage space? Like we already have two tables and we are creating one more data structure.
So this is where it helps. So if you have, like say, if you have 10 terabytes of data, but your instance size is 5 terabyte at maximum. Now, what do you do with the 5 terabyte? You just split it and put it in the second server. This is where the split will also come. Now the split itself is a contiguous row. So when you fetch a data, it knows that it's a contiguous range. Then it queries that range. Okay, and then it okay, the other part of it is a different server. So it will know that this split is here, this split is there.
The new split has this schema.
No, schema is defined by you.
So two table has two different schemas. Now,
So there are two tables, there are two schemas, two files in the hard disk or storage.
Not two
And then you have
tables.
interleaving, third, this is the interleaving is the third file, I guess.
No, there's only one data,
There is only one file.
only one file. Like you can think of it as a contiguous large file for the entire database.
Okay. So the example you have given is only of two tables. It may
Two
have
physical
three
servers.
tables.
It can be 10 tables, they can be 10 tables not interleaved together, it can be 10 tables interleaved amongst each other.
What if some tables have less rows?
That's fine. That's just, the splitting will take care of that. In the sense, it makes no difference, right? How about it? Yeah.
And the criteria for split is hard disk split only?
No, it depends on the many factors like CPU utilization, the amount of cache you want, your cache. Yeah, disk is one, of course, but right. Also stuff like keeping, even if your tables are not similar, don't have any relationship, you might want to keep the two splits together. Like if you have like a sales table which is not interleaved at all, you might want to keep it the same.
Similar to the kind of strategy.
Yeah, like the whole primary key will be short. Yeah, the primary key, for example, for singles, yeah, you need a single name, like ID or whatever. But for album, it is single ID and the album ID together with that as well.
And let's say there is leaking or update, let's say you do a mass position and then you can optimize. That must be a very costly process.
No, no, not really. I don't see why it will change any of the cost. The rows will just disappear, right? Because it's a contiguous range key.
So you
only that split will go away.
use multi-version kind of thing?
Yeah, we do have multi-version and we read snapshot. Oh, yeah, sorry. Yeah, you can snapshot read at any particular timestamp that you want. Assuming it's not garbage collected. Not the users. It's just managed in the background by an internal task that we have. Like ELDR is each group manages itself. Knows that I'm overloaded, so I need to give away splits. I need to split this existing split into two pieces. All of that. That group leader coordinates with its members and participants and decides that.
Can you go back to that? Yeah. So, you talked about
So you talked about this witness thing, right?
Yeah.
Third country. Can you talk a little bit about that? I mean, how it solves the problem?
Yeah, before going that, can you explain first the split part, how it works? Your last.
Oh, sorry. What was the question?
The split, like how you manages the split and who does the split, and from the customer perspective, you cannot see the customer data, right? How will you divide the split?
No, we do not manage the split manually.
No,
It's managed.
now only he manages the split.
Like it's automated, right? Each group manages itself. So the group knows when it needs to split, what it needs to split, depending on performance metrics.
Now the group here is the Paxos group we talked about.
Yeah, the Paxos group.
So the Paxos group also, see if you go to the Paxos group, it shows the process consistency between, like if any process fails,
Yeah.
it makes a consistency. But before going to the process, right? Like you have to chunk the data, right?
Yeah.
So who does that?
So it's a continuous range. There's no chunking. The chunking is just whichever range key chooses. Let's say you have a range of 1 to 10. Let's say you realize the 1 to 10 range is very hot. The group decides I want to split this into 1 to 5 and 5 to 10.
Group means like automated.
Yes. Yeah, group is just an individual unit of measurement that we have a zone master that does that. That decides like where each group goes. But yeah.
Okay. No, I have to read it.
Yeah.
Not clear.
Yeah, witness thing. Now, for the Paxos group to achieve on a single thing, we need to have consensus between the servers. I would talk about servers in a simpler term because that would again break down to the Paxos group. But let's say if you have 5 servers and you need to achieve one value. Now, if 3 says yes, 2 says no, how do you achieve consistency in that? So basically, there would be a witness there. Out of 5, 1 would be witness. Let's suppose it's a simple example. Now, if 2 says yes, 2 says no, what you will do? It's a 50-50 probability of yes and no. That's where the witness would come in and say, I would vote now. Because you are not able to achieve the consensus between you 4 guys, I would put my vote and achieve the consensus. Now, vote is not like a binary value, true or false, but it's an actual timestamp. Because again, it's a game of the timestamp. When you provide the timestamp, the reader will decide, okay, I have the highest timestamp and I will choose this timestamp for the commit.
This guy is in other country.
Yeah, this is an anomaly for specific reasons, because you need to keep both of the primary read-write replicas in the two countries of the same continent. Now you need to have consensus when from the third country as well.
And the last thing, where does this fall in CAP, this panel?
What?
The CAP theorem you explained, right? So the
Yeah.
database fall into which category?
So we guarantee consistency, and we reduce the amount of vulnerability by having like a very strong globally distributed network, plus having replicas across the globe. Yeah. Yes. Yes. And minimize availability with strong network and many array replicas.
Hi, can you explain the relation between splits and P groups?
So a group of splits form a P group. We form a Paxos group.
Got it. Okay. You also talked about having 3 read-write replicas.
Yeah.
So writes can go to any of the replica?
So each P group has a leader. It gets routed to that by leader way routing.
Leader will listen, will take the writes. And then they
Yes. Then they'll do a Paxos consensus and
Writes can go to any leader. So the leaders are spread across regions. You can write from Singapore and other like the applications hosted in Mumbai can write to the Mumbai leader. So it's all split.
Okay. And one small question. Instead of Paxos, wouldn't Raft have been more easier to implement over here? The Raft protocol. What advantage does Paxos give you over here?
That's a good question. But Paxos, we want to guarantee consistency across the globe, and we want it to be in a way that so we need a 2 timestamp, right? So we need to be XML consistent. So we need to be linearizable across the globe. So in that sense, we want consensus at the same exact point in time that all the world agrees, where US, India, and let's say Singapore all agree that at this point, this is the exact value. You can't do that in Raft.
Okay, got it. Thanks. Yeah.
Exactly. You need to guarantee a timestamp that the world agrees on.
And when you do this about the leader aware routing, how do you track this leader data across the globe? Like, do you cache it, or how do you keep them consistent?
So we have something called Spanner API frontend, which directs our request to the Spanner server. Now, the Spanner server itself would decide who's the leader, but its information is available to the Spanner server. Now, Spanner API frontend also knows about its leader, like which leader it was, so that it can forward request to it. Now, Spanner API frontend knows this, then it would forward the request to the leader. So we already have this data in the Spanner API frontend. So now the question comes is, we need to forward this for correct Spanner API frontend so that it forward its request further to the Spanner server. Now all this happens, but we keep it an internal table to keep track of who is the leader. Now, what if we expose or provide this data to the client itself, so it knows which Spanner API frontend talks to which leader. So it is generally cached in your client side library. No, client side library. So it's already cached at the Spanner API frontend, but it would also be cached in your client library.
Client can be anywhere in any DC. It need not be just Google.
Exactly. It can be anywhere. It can be your phone, laptop, another data center.
Yes. So one question, like you tell that global time consistency you maintain across all the stack, right?
Yeah.
How you do maintain that? Let's say it's a front end is in the client laptop, right?
Yeah.
So how you maintain
The
that?
client does not need to maintain the global timestamp, but Spanner API frontend, not the Spanner API, but all the servers at Google would have a global consistent timestamp. So that is provided by the TrueTime API. So this, you can think of this as a GPS clock system or another clock system. So basically, if I would were to give you a very naive analogy, is that have you seen the ntp. Google.com or Microsoft.com? It would be similar to that API. It would just provide you the timestamp.
The timestamp of the server or timestamp of the data?
The current timestamp.
Yeah, current timestamp. Let's say in a different geographical region,
Yeah.
you have a cluster here, another cluster in another continent.
Yeah.
How you maintain a consistent timestamp?
Okay. So even if two servers are geographically apart, if you consider a simple case where UTC 00 would be same at both the location.
Yeah, but when your write goes, let's say from a geographical X to geographical Y.
Yeah.
So let's say there is a X amount for the travel, then how you write in the same timestamp in the other region?
So that's where the commit wait is there. So commit wait is basically a small lag time or the wait time which is there. Now, consider an example where, as you said, the write goes from one region to another region. So this write goes from one API frontend to another API frontend. Now this API frontend itself initiates the transaction.
So every API call, you maintain that commit time, you mean to say?
Yeah, you
because see, it's a global region replication, right?
Yeah.
Because multiple, it takes X amount for this, right? But for another write, maybe it coming from another region to this region. So every transaction, whenever it passes for a replication, do you send a timestamp saying that this is the timestamp I have to write? No, that is the timestamp server will maintain. That is not the problem. Let's say you write into X replicas X cluster in a timestamp called X.
Yeah.
Another cluster is in a geographical R. It takes 10 minutes to go there. Am I right?
Yeah.
How you maintain this consistency for every write? Because write can be going to any of the cluster.
So only the servers, only the Google servers need to maintain that timestamp, right? So when you query to time, you get a window of time that this commit can happen in, right? So only that matters. The end clients, your actual end users, your Kubernetes VMs or your pods or those don't care about that. So all they get is a commit response being okay and a timestamp at which will commit it happen. So only the log on the servers matter.
Any white paper on this?
Yeah, there's a Spanner white paper.
Can you show the?
Yeah, we'll add it to the slide deck.
Yeah, we'll add it.
So I have one question about the write operation that we perform in the true time. So how do we control the versions of rows, like multi-version concurrency control kind of thing in Spanner?
So the one-word answer would be snapshot. You create a snapshot of the one row, and then you can read the snapshot.
Okay, so is it not like what the Postgres does for write operation on any row?
Say it again.
No, so I was comparing how the Postgres maintain the version concurrency of any row and how this.
Yeah. So in Postgres, the snapshots are a bit different. I think these are different, same words, but different meaning. So in Spanner, we just append log. All your rows are append logged with a timestamp when it was written. So if you query a row 5 minutes before, it looks for the data that was written 5 minutes ago when you're going through the append log. And of course, there's compaction and stuff to keep this append log small, but yeah.
Okay, yeah, thanks.
I have a question. Like you said that when a particular group gets overloaded, it creates new split and hands it off to something else. So I'm assuming there would be a lot of groups all busy, right? So does it provision a new group on the fly, or how does it identify a group who can take on that load?
Yeah, new groups keep getting created all the time. And there's always dozens of groups being created, deleted, merged, all of that happening in a database.
And who's orchestrating this?
So we have each zone has a zone master that will take care of that.
So it keeps monitoring all the loads of all the groups and basically predicts that it would need to spin up a new group.
So each group takes care of itself, and the zone master just ensures all the groups in that zone has someone is being hosted somewhere on some server. If some server is down or the group is NLT, it moves it to a different server. That's all the zone master does. But each group, if it gets overloaded, it splits itself. and creates its own, it gives off splits, divide splits, all of that normal stuff.
So when a group splits the data and creates a new group, right? How does it basically, does the group provision the new group, the new peer group who's going to take the handover? Or is it the zone?
Yeah, you can think of it like that. Yeah, the group, that group creates new groups. Yeah, so somewhat like that.
Group will basically create another group. Okay.
Yeah.
And it will also register with the zone master for further health monitoring.
Correct.
Good.
In the last question.
Yeah. Hello. Okay. So you are using your true time, which is your in-house timestamp. So why did you choose this instead of epoch time, and what were the limitations you were facing with epoch?
So it is epoch time. It's just how we get that epoch time. If it's like NTP or something, inherently NTP has a few milliseconds of delay. Like if you say, like if you have a single NTP server, synchronizing that with an India and the server synchronizing the US, just because of network delay and a lot of routers and everything between, there's always going to be a few milliseconds. Even however hard you try, maybe you can bring it down to a few microseconds, that's it. But then true time gets you from satellites and atomic clocks that managed in Google data centers that are guaranteed to be synchronized across the world. And yeah, because that's very important that we get very little skew between that, because our commit rate is governed by how fast we can generate timestamps.
Okay. So for time synchronization, you are using satellites.
Yes, satellite atomic clocks in our data centers.
Okay.
One last question about interleaving tables. So when you modify a schema, let's say you add more relationship to an existing table, does it impact your data partitioning and all? How does it work? Because you keep the data together, right? I mean, related data.
Yeah, we keep the data together. So when you modify your schema, it has to do the modifications to all the groups as well.
So I add a new relationship, let's say.
Yeah, I think schema changes are complex. I think we are almost at lunchtime, so we can talk about schema changes separately offline.
Hey, guys, we will take the questions more into the Discord channel or the Meetup. Sorry about that, we are running behind the time. We will do a lunch break now. 2 o'clock, we will start the next session. After the lunch, while coming inside, please collect your swags. So we have a counter set up. So after finishing the lunch, you can come back and collect your swags. Thank you so much.
When you say like we're calculating at 2 times, so is it its threshold or what? Like won't like it?
Lunch is at across the
So 2 times
floor.